All right, let's dive right in. In this explainer, we are taking on something absolutely mind-blowing. We're going to decode the exact recipe of our entire universe. And the wild part? We're going to do it just by looking at its oldest light. We're talking about the cosmic microwave background. Think of it as our cosmic Rosetta Stone. We're going to see exactly how these unimaginably tiny variations in ancient light let us understand the fundamental components of reality itself.
You know, for decades, cosmology was kind of just a field of incredibly bold speculations. But by observing the cosmic microwave background, scientists have actually transformed those wild ideas into a rigorous, working cosmological model. We aren't just guessing anymore, we are actually measuring.
So, what exactly is the cosmic microwave background, or CMB? Basically, it's this incredibly uniform ancient light left over from the early universe. But here's the thing, the real secret isn't in the uniformity, it's in the imperfections. We're going to analyze the microscopic smudges or temperature ripples in this ancient light to track down the exact culprits that caused them.
Okay, so here is our game plan for this explainer. First, decoding the cosmic fingerprint. Second, the universe's first symphony. Third, the recipe of the cosmos. And finally, fading echoes and polarization. Let's jump into Chapter 1, Decoding the Cosmic Fingerprint, Reading the Universe's Oldest Light.
To even read this fingerprint, you really have to appreciate the absolutely wild level of precision we need. I mean, this CMB light is cold. We're talking an average temperature of roughly 2.728 Kelvin across the entire sky. It's essentially a near-perfect blackbody. But to find our cosmic fingerprint, we aren't looking at the whole average picture. We are hunting for microscopic variations, fractions of a degree so small, it's literally like looking for a single grain of sand that's slightly warmer than the rest of the beach. We are measuring differences on the level of 10 to the negative fifth from one tiny patch of the sky to another.
Why do we care about a fraction of a degree? Well, look around today. Our universe is super clumpy, right? It's filled with galaxies and these massive clusters of matter. But the early universe, the one represented by the CMB, had a remarkably smooth photon distribution. That massive difference is there because radiation pressure kept the early universe smooth, totally preventing photons from clumping together. It gave us a perfectly clean slate. And because it was so pristine, physicists can use really simple linear math to trace these tiny ripples backward in time, completely bypassing all the messy, chaotic astrophysics of modern galaxies.
And that brings us to Chapter 2, The Universe's First Symphony, Sound Waves in the Cosmic Plasma.
Picture this. Before the universe cooled down, it was this wildly intense, tightly coupled fluid of light and matter. And it went through this dramatic mechanical cycle of acoustic oscillations. First, gravity pulls the fluid down into these potential wells. But then, radiation pressure fights back. It resists that pull, causing the fluid to compress and heat up. Eventually, that pressure just becomes too much, and the fluid dramatically rebounds outward, cooling back down. The early universe literally rang like a giant bell, just oscillating back and forth.
If you were to catch these sound waves at their absolute maximum compression or their maximum stretch, at the exact moment the universe cooled enough to finally form atoms, a moment we call recombination, boom. They match directly to the peaks in the CMB temperature data we observe today. They're literally sound waves frozen in time.
All right, Chapter 3, The Recipe of the Cosmos, Finding the Ingredients in the Acoustic Peaks.
So what's in the cosmic pantry? Here's the inventory we're hunting for. Photons, neutrinos, baryons, ordinary matter, cold dark matter, and dark energy. Our job as cosmic detectives right now is to figure out exactly how each of these ingredients leaves its own highly distinct sonic signature on the CMB.
Let's start with the very first acoustic peak. It's absolutely crucial. The apparent size of these sound waves would be totally distorted to us, like looking through a cosmic funhouse mirror if space itself were curved. But the fundamental scale of this first peak perfectly matches the prediction for a straight, undistorted path, which proves once and for all that our universe's geometry is flat.
Now we can start hunting for ordinary matter, the baryons. Check out how those alternating oscillations change their amplitude. Because baryons provide extra inertia, they act exactly like a mass attached to a spring in a gravitational field, actually shifting the 0 point of the oscillator.
To expand on that whole mass on a spring analogy, because baryons have mass, they enhance the compression of that fluid into the gravitational potential wells. So the more ordinary matter you have in the universe, the further the spring falls. That drastically boosts the amplitude of every odd-numbered peak, like the first and third ones, relative to the even-numbered ones. By measuring these peak heights, we are quite literally weighing the normal matter in the universe. Okay, but what about the dark matter? Cold dark matter doesn't experience radiation pressure at all, so it just doesn't bounce. If the universe were dominated only by radiation early on, the gravitational potentials would decay, driving up all the oscillations. But the fact that we see a prominent third peak, that acts as a definitive fingerprint. It proves the dominance of cold dark matter. It was the invisible anchor that kept those gravitational wells totally stable when everything else was bouncing around like crazy.
So, we've got this incredible, vibrant symphony ringing out the exact recipe of dark matter and baryons. But it brings up a huge, fascinating question. What actually happens when all that cosmic music finally fades away? That brings us to our final chapter, Fading Echoes and Polarization, where we'll look at diffusion damping and the final scattered light.
As the universe expands and cools, that tightly coupled perfect fluid begins to break down. We get an effect called diffusion damping. Imagine dropping a bit of ink into a glass of water and watching it blur as it spreads. As photons slip past the ordinary matter right around the time of recombination, they travel from hot regions to cold regions, which effectively washes out the very small-scale temperature ripples. That's exactly why the acoustic peaks die out at smaller scales.
But here's the cool part. This fading process isn't just a loss of data. No way! It creates an entirely new data set. As photons and baryons decouple, the light scatters off electrons in a process we call Thomson scattering. If the incoming light has a specific cross-shaped temperature pattern, this scattering generates a small but highly measurable linear polarization in the light. It literally gives us a completely independent check on all our cosmic math.
We classify this polarization into two different flavors. First, E modes, which naturally align with the standard density perturbations, those sound waves we've been talking about. But then there's B mode polarization. B modes twist at a 45-degree angle, and they are entirely different. Standard matter ripples simply do not create B modes. They are incredibly elusive. Which leaves us with this final, thrilling prospect for the future of cosmology. If standard density waves aren't making these B modes, what is? The answer is gravitational waves, from the literal dawn of time, right at the moment of inflation. Could finally detecting this elusive B-mode polarization be the ultimate key to unlocking the universe's absolute first fractions of a second? That is the next massive frontier for the CMB, and I really hope this explainer has left you as pumped about it as I am. Keep looking up and keep questioning the cosmos.